So we have seen many examples of categories so far, yeah, and some categories are spatial. I mean, just the way graphs are built, yeah, graphs are built with vertices and then arrows. So, I mean directed graphs. Whenever I say graphs, then directed graphs. So in a similar fashion, I feel like a category can be generated out of thick points and thick home sets. So basically, if you look at this, the spread of the category, that is captured by this pre-order. Yeah. So pre-orders will say that they are thin categories, so they capture the spread. From where can you go to where? Yeah, that way. So the objects themselves don't really play any role. Yeah, the objects only have one endomorphism, namely identity morphism. And if at all the home set is non-empty, then it is just a singleton. Okay, so they talk about spread, whereas this example number 6, which is about monoids, yeah, that is something to the other end, that you have taken one point and you have added too many endomorphisms, but there is only one object. So this is about thick and thin parts, okay. So in some sense, I feel like these are the two generating examples for all categories, two basic examples. Okay, so one example, like two examples that we saw last time, and we haven't really described them properly. That is the category of small categories and the category of locally small categories. And where we said that the morphisms between categories are functors between them. Okay, so what are these functors? The definition is quite simple. So functors you should be given two categories, yeah, then only you can define a functor. So given categories C and D, a functor f from C to D is given by the data of. So what is the structure? Yeah, I mean the structure and properties, that distinction is always going to be very crucial. So if you remember, the structure of a category is the collection of objects, the collection of morphisms, the identity maps, domain, codomain and identity, and finally the composition. Okay, so this is given by the data of, well, first thing, an object Fa for each object A of C. So an object should get mapped to another object. Then a morphism FF from Fa to Fb for each morphism F from A to B, I mean this morphism in D for each morphism F from A to B in C. So basically this is saying three different things. It's not just saying that morphisms get mapped to morphisms. It's also saying that the domain and codomain are preserved. Okay. And composition, so whenever and if for F and G in mor C, the composition GF exists. I will sometimes write a circle between them, sometimes I won't. I will just write juxtaposition, composition. Then what is the image of GF? That just has to be the composition of the images. So basically the composition has to exist, which will automatically be true by the second condition, yeah, and this holds. Satisfying, yeah, oh, one more thing, for each object A of C, what is the image of the identity morphism? Identity of the image. Yeah, so 1 sub Fa. So identities map to identities, composition to composition, objects to objects, and domain, codomain, morphisms, everything just to appropriate locations. Now functors, if you look at them, then I mean, you can obviously compose functors, yes? Yeah, because if you are taking this category C, then this category D and this category E, then you will always map it here, then you map it here. So then composition of functors is naturally going to give you a functor. Then there is also identity functor on each category. What does it do? It takes objects of that category and maps it to itself. Then it takes morphism, maps it to itself. So composition is automatically preserved, identity is preserved. So far what I described to you is the structure of, is the categorical structure of the category cat. So it's simple. Yeah, I mean, therefore there is no Russell's paradox here. The collection of all categories, I mean up to any collection, I mean here we are talking about small categories or locally small categories, but that will again be a category, and that's important. And functors are ubiquitous. Yeah, this word, get used to that. Ubiquitous means present everywhere. Yeah, they are omnipresent. Ubiquitous means they are omnipresent. They are present in all areas of mathematics. So today our goal is mostly to look at different types of examples of functors. And you simply start in any field and you will find so many examples of functors. And they are very natural examples of functors. So let us start. So examples of functors. Now newbies always make a confusion. Did you say function? When I say functor, then they ask whether it's a function. But actually all functions are in fact functors. Okay, so that's our first example. How do we, I mean, what is the domain of a function? A set, exactly. So it's a set. So set we have seen can be treated as a category. It's a small discrete category. So let us look at that. So suppose A and B are small discrete categories. What is the meaning of discrete category? Only morphisms are identity morphisms. Very good. So out of all these definitions, all this data, what has to be preserved? Objects should go to objects. So what are objects? Objects are elements of the set. So elements should go to elements, identities automatically go to identities, and there are no other morphisms to care about. So basically just that much data. So then a functor f from A to B is simply a function. Okay. Now another thing, suppose M1 and M2 are small monoids, are small one object categories. Then a functor f from M1 to M2, what will it do? It will take that object to that object. Yeah, there is nothing to do there. But it will take a morphism to a morphism. So basically it's taking an element of one monoid to another element in such a way that the identity is preserved, right? And composition is preserved, so that multiplication is preserved. So it's just is a monoid homomorphism. Homomorphism is just HM. Okay. In particular, groups, if M1 and M2 happen to be groups, then it will be a group homomorphism, right? And even if G1 is a group and G2 is just a monoid, then what will happen? It's a monoid homomorphism, but it will, like, the elements of the group will only map to invertible elements because there is some identity. Yeah, if M1 happens to be a group, then for every f there is some g such that gf is equal to identity equal to fg. Okay, so in that case gf and fg are, equal to identity. This equation has to be preserved by any functor. Okay, so every functor preserves equations. So that's what you should keep in mind. So therefore, invertible morphisms will always go to invertible morphisms. In particular, what I am saying, that all isomorphisms are always mapped to isomorphisms under functors. So I'm just going to write it as a property. If f is an iso in a category C and f is a functor, then ff is an iso with, what is the inverse of ff inverse? Correct. The only logical choice that you have. Yeah, so this is just a side remark. Okay, so suppose P1 and P2 are posets, means partially ordered sets. Then a functor f from P1 to P2 is, what do you call it in a monotone map? It preserves order. Why? Because poset is a pre-order. Pre-order means the home set is non-empty. If it is non-empty, then the corresponding home set also has to be non-empty. So you can see how beautifully all these different spatial cases come under one umbrella. Those who are looking at category theory for the first time, would you have thought that monoid homomorphisms and monotone maps are just two spatial cases of the same construction? Okay, so is a monotone map. Monotone means order preserving map. Okay, so here I can also put pre-orders. Yeah, it doesn't have to be a poset, it can also be a pre-order. And still the idea will work. Okay. Now we are planning to go ahead and introduce some large categories. The fourth one is perhaps familiar to some of you, at least. Suppose G is a group. Then a functor F from G to the category of sets is, what do you call it in your everyday language? No, it's not a forgetful functor. It's a functor from G thought of as a category to the category of sets.
A group action, a G set.
It's called a permutation representation. Okay. So what is happening? How many objects does G have? No, how many objects? Cardinality of G is how many morphisms there are. There is one object. One object. So one object has to map to one object. So one set. So functor must send that unique object to some set. Then what else is happening?
Getting embedded in SN.
It's not getting embedded. There is no SN over here.
The set of invertible.
Set of invertible maps. Yes, correct. So you are mapping this single object to a set. Yeah, so let me write it. Yeah, usually this is a helpful way. So suppose I am mapping it to set X. Then I have some morphism. Every morphism is an endomorphism in a group. So this thing is also getting mapped to X, and this is some element of the group, let's say G, and this G will also get mapped to some element, and I am calling it Fg. Okay. But what is this Fg? By this remark star, yeah, the remark star, it says that every invertible map, because every element in the group is an isomorphism in this category G. So therefore it will map to something invertible. So that is an automorphism. I mean automorphism or a self bijection from X to X. Right? So it's the symmetric group of self bijections of X. So basically what you obtained is a group homomorphism from G to the symmetric group of X is simply a group homomorphism from F from G to sim of X for some X, for X equal to F of this unique object. So this is called a permutation representation. This is a permutation representation of G. Okay. Now, if I change the category of sets to something else, yeah, I am going to do that on the next slide. Yeah. So, a functor, it is still in the same example, a functor F from G to, let us say, R vector spaces. What will it give you?
The endomorphisms, a group embedding of G into the endomorphisms.
There is no embedding happening here.
Yeah,
I never said it's an embedding.
I mean the endomorphisms of a particular vector space. So
Endomorphisms of a particular vector space is not a choice. I mean that's too big of a set. They have to be automorphisms. Isomorphism is also not a, I mean isomorphism of what with what? V to V. So that's automorphism. Yeah, the name for that is automorphism. So this is called a K linear representation, R linear representation of G.
So why can't it be thought of as a embedding? Because
Where is embedding coming into picture?
image of those maps is a subgroup of the automorphism of that vector space. So that is the embedding.
That's embedding means it has to be injective, but where is it injective? So what about me choosing zero vector space? If I choose zero vector space, then what is the automorphism group of zero vector space? Just the identity. So now it's a group homomorphism from G to the trivial group. Now it's a homomorphism. It's not necessarily an embedding. Okay, so it's just called an R linear representation. If you change it with any ring R and then mod, then it is again, it's called an R linear representation. So representation theory is study of some functors. Okay, if you are interested in representations of groups, then that is, I mean, either it's, it's the same thing. You usually map it to vector spaces, yeah, because we believe that we understand vector spaces better than we understand groups. So that's why this is the right thing to do. Okay. In fact, we are going to see later that there is a category of all functors between two fixed vector space, two fixed categories as well. Yeah, where the objects themselves are functors, and there will be morphisms between functors. Okay, so which we call natural transformations, and that will be the category of all R linear representations of a group, fixed group. So you are again studying a category of functors. Any questions? Okay. So this idea can be made general. In fact, towards like the end of the course, we'll also see that R mod, the category of modules, is also a category of functors. Every module is a representation. Okay. So now let me make this open. Can you give me some examples of functors where you are taking a fundamental group? Very good. So let me check. This is number 5. So fundamental group of what? No. Connected topologicals. Path connected. Pointed. Pointed is important. Connected, path connected, I mean that depends on. So this is pi 1. Pi 1 is a functor from top star to groups. Okay. So here every x comma x naught will get mapped to pi 1 x comma x naught, and any continuous base point preserving map will induce a group homomorphism. So it behaves well with respect to the natural maps present in top star, and therefore this is a functor. More generally, you have a fundamental groupoid. Yeah, that is pi 1, and that goes from top to GRPD, the category of groupoids. Yeah. Now, in fact, we can also do something else. Pi 1 can also be thought of as, like little pi 1 can be thought of as a functor from a quotient of top star by homotopy equivalence classes of topological spaces, base point preserving homotopy equivalence classes. So here I can also say this is HTPY star Yeah, you understand HTPY star? So there are two pointed topological spaces, and there is a homotopy between those two spaces which preserves the base point. Homotopy equivalence between two spaces. Yeah, which is just a pair of maps in opposite directions such that the compositions are homotopy equivalent to the identity. Okay, so fundamental group, this is a natural choice. Yes, any other examples of functors that you can think of?
Forgetful functor, like from an algebra to a vector space.
Forgetful functor, okay, good. So, okay, forgetful functor, what does it forget really?
Any structure which we want.
Any structure that we want, okay. So, let me ask you, is this a forgetful functor from groups to sets? Yeah, the usually forgetful functors, it's customary to denote them by U. Okay, U for underlying. So, a group is G, then some multiplication, some inverse and some identity, and you forget about MIE and you just map it to G. Yeah, that's a forgetful functor. But can I say that the natural map from abelian groups to groups, is that a forgetful functor? No, why not? It's also forgetting something. It's forgetting abelian structure. It's forgetting a property. It's not a forgetful functor. If you are forgetting a property, then you usually get inclusion functors. Yeah, not forgetful functors. So let me simultaneously write this other class. Okay, so this is inclusion functor from the category of abelian groups to groups. What about monoids and groups? All groups are monoids. That's an inclusion functor. Aren't we forgetting the inverse part of the existence of inverse is a property, correct? So therefore I should write inclusion from the category of monoids to the category of groups. I mean, I can also write it like this.
So, but while writing groups, we write two maps as the property of groups, like the multiplication map and the inverse map.
Yes, I mean that's a choice of language, but that doesn't mean that if you know M and M has the property that there is an inverse and there is an identity, then you can't really forget it. Even if it is not explicitly given, it still has the property, which is what makes it a group. So basically it's automatically a monoid.
So, is there a concrete definition to
What constitutes a property and what constitutes a structure? Yeah, I mean definability. If yeah, so let's not go into that. So groups to sets, yeah. Then what if we take the category of rings? What can we forget? We can forget multiplication, and what do we get after forgetting multiplication? Abelian groups. Or you can also forget addition, and then you will get, first from here you will get monoids.
So you are taking the unity always.
Yes, it's I, RING. So I stands for identity, so it's present. Otherwise I would write RNG. Okay. And then from both of them I can get down to the category of sets by forgetting about every piece of algebraic structure there is. Okay. Another thing that we can do is go from topological spaces to the category of sets. So you simply forget about the topology. Yeah, that's a valid forgetful functor. You are actually forgetting structure here. Yeah, topology is not a property. So you are forgetting it. Metric space to topological space. What will it be? It's also
It's none of them.
metric, existence of a metric. You are forgetting about that.
Yeah. Okay.
Yes, so this is also a forgetful functor. Very good. So these are all forgetful functors, metric spaces to topological spaces. Now, when we are looking at it for the first time, it might seem meaningless to forget about some structure, but it's actually quite useful.
What about the metric?
Uh-huh.
How the topology is defined?
I mean, you can always remember the derived topology from the metric. I can also write normed spaces, normed vector spaces behind that from a norm you can get a metric. I can also write inner product spaces. From inner products you get norms, from norms you get metrics, metrics you get a topology, and from topology you forget about everything, you get a set. So actually this is a very important notion in mathematics, yeah? That we forget about parts of structures, and that will become clear as we go along. And what about, let's say, commutative monoids and monoids? That's an inclusion functor. Yeah, just to make sure I have a name for it. Yeah, I'm writing it. Then similarly, commutative rings and just rings.
So I have one.
Yeah.
So when we are taking the inclusion functor from monoid to group, so will that not be from groups to monoid, since every group is
Oh yeah, sorry. Yeah, obviously. I'm really sorry about that. It's from category of groups to category of monoids. Thank you. And this one further we can include into semigroups. Yes. That was just a righto, not typo. Okay.
You can get the commutative monoids from abelian groups, right? By
Commutative monoids from,
abelian groups.
and how do we do that? You can get commutative monoid from.
By way of an inclusion functor in a similar way from groups to.
Yes. So you want me to write it here? Commutative monoid to abelian groups or abelian groups to? Huh, right. Yeah. So I mean I should write it here. Yeah, and here. Yes, thank you. I can in fact get rid of these notations, but usually for inclusions we'll use I.
Sir, from monoid to semigroup,
Uh-huh.
we are forgetting the identity and it's the structure.
Is it?
Because it comes with the
You have, I'm sure you have shown that property. Is it possible for a semigroup to have two different identities? Like that multiplication in a semigroup has an identity, that's a property. It only depends on property. Yeah, therefore it's still an inclusion functor. I mean, these are certain things to prove actually. Another thing where we have been talking about this pointed spaces, so set star to sets. You simply forget about the choice of the point. Top star to top. These are forgetful functors. Then, well, you can also consider something more complicated like a topological group. A topological group is a topological space together with a continuous binary function defined on it, such that the inverse for that is also continuous. Okay, So it has got two different structures. It's a group, it's a topological space such that these M and I are continuous maps. M is a map from G cross G to G, and G cross G has product topology, so it is continuous, and I has a map from G to G that has. So from here you can go to top,
So
or
now if we define a map from like topological group to like we define a topological monoid, then will it be considered a forgetful functor or an inclusion functor? Because now we have an I which has a significance.
which has a significance, but
Because we have to define a continuity.
Yeah.
we have to define continuity. I mean, continuity is also a requirement.
Yeah, but like we can't. I mean, I cannot be just thought of as a property here. I is a structure.
That there exists a continuous inverse.
Yeah.
Okay. I mean, that depends on how we are looking at things, isn't it? If every single map that we consider has to be continuous, if that's our understanding, then perhaps it will just be a forgetful or inclusion, or otherwise, if you also allow other functions, then it will be.
If we say this is a property, then this property comes from some structure in that space, but continuity having
Continuity also comes from some no. Okay.
in that structure.
Right.
Isn't the identity defined?
Inner, I mean, it may be definable in the language of groups, but topology, which language are we talking about?
I mean, this is an inverse map. It's not identical.
Yeah, I mean, yeah, inverse map, but topology. Okay, if our language doesn't allow that, then we will treat it as a forgetful functor. Okay. Okay, so now we have got some obvious things. Yeah, forgetful functor like you and inclusion functors, you are forgetting about some data that you already know. Now we are going to look at examples which go in the opposite directions, where we are trying to introduce new kind of spaces in the most general way possible. So for example, yeah, let's start with this. Can you describe a functor from sets to top? If you are given just a set, can you equip it with, I mean, can you associate to it
We can associate it with a
discrete topology? Yeah. So I am writing it tau disk. Okay. Is that the only choice? Indiscrete topology. So tau discrete is every single subset is open. So power set. And there is another functor also which is tau indiscrete, where only the full space and the empty space are open and nothing else. So this is an obvious choice. Okay. So this type of functor is called a free functor. Yeah, we are trying to introduce some structure on our original structure, on top of our original structure. So what about, let's say, sets to abelian groups? Does there exist a functor given a set X? I mean, one thing, yeah, just a moment. One thing you should notice that we are not just doing it at the level of objects, okay? If we have two sets X and Y, then a function between them will also be continuous under these two topologies. Yeah, if you equip X with discrete topology, then every function is continuous, and if you equip Y with indiscrete topology, then also everything is continuous. So both these properties are being used. Yeah, that's always taught in a basic topology course. Yeah, if the domain is discrete, then inverse image of anything is always open. And if the codomain is indiscrete, then there are only two things to check. Yeah, so we are using both of those things. Yeah, sets to abelian groups.
Taken the abelianization of the
Abelianization
free group on that set.
of the free group. Okay, you are describing two different things at the same time. So you are also describing this. So this is the free group.
Yes.
Okay, so X mapping to Fx. So let us remind everybody of what the free group is. So free group means you take symbols. Yeah, we are trying to form words with elements from capital X and formal inverses. Yeah, so free group is you take words with alphabet, finite words, yeah, I mean that's important, finite words with alphabet X and X inverse, which is simply A inverse for A in X, and up to identification A inverse A equal to AA inverse equal to epsilon, where epsilon is the empty word. For each A in X. Okay, so this is what we do. So that's a free group. And what is the operation in the free group? Concatenation. Okay, good. Okay, so he said take the abelianization of the free group, but there is also a simpler explanation for sets to abelian groups. As a Z module, yes. What Z module?
Z linear combinations of elements of the set.
Z linear combinations of, right, X indexed finite support functions. Very good. So I mean over here what is happening, that X is getting mapped to, I will just write this, direct sum of capital X many copies of Z. So these are all finite support functions. Yeah. And if you have a map from X to Y, then automatically that induces a map between these two spaces. What do? You are given a tuple. How do you deal with that tuple?
So the map will be from, let's say, for a copy of small x in X.
Uh-huh.
So it will be mapped to some f of small x, which is in the form of y.
F of small x, correct? Correct. Right, so the map is induced by action on the index sets. Yeah, the most natural thing that you can do. And similarly for free groups also. What do you do in case of free groups? You take those words, on each entry in that word you apply F.
You just extend that function to the.
You extend that function. Yeah, you apply F to each element of the alphabet, and if it is of the form A inverse, then you take F of A whole inverse, which is another symbol. And then if there are some cancellations to happen, then you cancel them out, and then whatever is remaining, the reduced word, is your final answer. Okay, so that's how these both of these are actually functors. Okay. Okay, so now let's look at some more examples of this kind. So what about sets to preorders? Can every set be equipped with a preorder relation? Smallest reflexive relation.
Diagonal relation.
Diagonal relation, okay. So that's x comma delta x. Yeah, I'm writing delta x for the diagonal relation a comma a, where a belongs to x. There is also another possibility.
We associate everything with.
Right, x comma x cross x. There are too many x's in this, but I hope you can understand. Okay, so x cross x, so x square. Everything is related to everything. Okay, then can you do the same thing with posets also? Like a set mapping to posets.
I mean x to delta x is a poset.
That is a poset, correct. So in fact I should add one more example, yeah, posets and preorders. The category of posets to category of sets. That's a forgetful functor. You forget about your operation, your relation, order relation, and similarly you can do preorders to sets. Okay, then there is another type of examples. Now this is happening from the category of preorders to the category of posets. I mean partial orders, let me just say partial orders. Yeah, not because it's not necessary that they are sets, just from preorders to partial orders, and this mapping is the quotient. So if I am given a preorder p less equal, then I am going to map it to p less equal quotiented out by less equal intersection greater equal. Less equal intersection greater equal means the things which are equivalent. This is less than this is less than this, so they are equivalent. So if I reduce, I mean these are redundancies, yeah. If I remove all the redundancies, then whatever I get, that will be a partial order. So for example, yeah, I mean if you are confused about this, then let me say I have got three elements A, B, C. This is my P. Then I can say my less equal is defined to be this, that it consists of A is less than B, A is less than C, B is less than C, and C is less than B. Okay, so all these things are given. Now what will be the corresponding partial order? Are B and C actually different here? No, they are not equal. They are definitely different, but you can identify them because their relationships with other elements are exactly identical. So we are taking a quotient. Okay, so this is, I mean I am just going to call it the posetal reflection, the partial order reflection. Why it's called a reflection, we will come to that later, but this is called a partial order reflection functor. Yeah, so less equal here, let me just complete it. So this will be BC and CB. So you have to quotient out by this relation, and of course I mean, oh, I did not mention AA, BB, CC. Yeah, that has to be considered as well. So here also I will add BB and CC in this collection, and then I take the quotient. Okay, so basically B and C are identified and it's just a two element chain. Now In a similar fashion, I can give you one more interesting example. So let us start with cat, and I am going to assign to it one pre-order. I will take a category C, and it's a small category. Yeah? Cat, I have written small at, so small category. So take the objects, collection of objects of C, and equip it with a less equal relation where for A and B in objects of C, A is less equal B if and only if the home set in C of A and B is non-empty. If that home set is non-empty, I will make it thin. I will just retain one single morphism, and I will get rid of everything else. So by transitivity, by compositions will transform into transitivity. Identities will give you reflexivity. So we are indeed in this pre-order. This is called a pre-order reflection. And you can also do it with CAT all caps.
So we can think of it as a forgetful functor because
Are you really forgetting anything?
yeah,
No,
composition,
no, no, no.
data compositions.
That's not part of structure. Data of composition, whether it is empty or non-empty, that's
I mean, there can be multiple automorphisms on an object.
no,
It just reduces it to.
no, it's definitely not part of structure.
So what is its part of, like?
I mean, we are detecting something, whether it is empty, whether particular home set is empty or not. That's what we are detecting. I don't see why this should be a part of structure.
So is it an inclusion functor?
No, I said it's a pre-order reflection. It's a reflection functor.
I mean, we are losing some information, right? In this functor.
When I will explain reflection functors, maybe we will come back to it. Actually, there is another thing which I should write perhaps now that we have talked about it. Then from cat, from pre-orders to this capital cat. Oh, sorry. I should write it under here. Pre-orders to cat. This is actually an inclusion functor. Yeah, every pre-order is a category first, and it has some properties, and that property we are forgetting to just remember that it's a category. Okay, so at this point perhaps I should point out one interesting thing about, so this is a note or a remark, that suppose this is an equivalence relation on the collection of morphisms such that whenever F is equivalent to G and H is equivalent to K, FH and GK are composable, I mean exist, are defined, then FH is also equivalent to GK. Then we say that this is a congruence relation on Morse, and C quotiented out by this is a quotient category of C. So there is a functor from C to C mod this. Now we have already seen such examples, construction of HTPY from top and construction of this pre-order reflection from a category. They are both constructions of this kind. In this case, actually, what is our relation? That F is equivalent to G if and only if domain of F is equal to domain of G and codomain of F is equal to codomain of G. If we take this as your relation, then you quotient out by this congruence relation and you will get the corresponding pre-order reflection. Yeah, so this is a quotient construction. Yeah, this is for pre-order reflection.
Quotient rings can be thought of as this construction.
Quotient groups, definitely. Yes, quotient rings, I don't want to talk about them just yet because we haven't done additive categories. Yeah, later on we can say that. Okay, then some other but still interesting examples of functors, which, well, I will write them down. So this is R vector spaces, but I am just putting a condition that they are finite dimensional. Then from here, R vector spaces with a fixed basis, okay, fixed basis, and then I am mapping it to mat R, and every vector space with a basis will get mapped to simply the dimension of V. Now this is a functor, and what will be the corresponding matrix in the image?
Standard matrix like
Yes, we are given fixed basis, so with respect to them, this particular linear transformation will have a matrix, and that will be the matrix in the image. Okay, so this is another example. Then if you have done algebraic geometry, commutative rings and its opposite category, yeah, we haven't yet talked about this, two category of topological spaces. So if you take a ring R, then the Zariski spectrum, that is also a functor. Okay, those who do not know about it, Zariski spectrum is the collection of its points. Yeah, points of this topological space are prime ideals in prime ideals of R, and if you are given a morphism, a ring homomorphism from R to S, then in fact you get a map in the opposite direction. Yeah, this is called, I am just going to write it as spec F, and this happens because for any prime ideal, P of S, F inverse of P is prime in R. Inverse image of a prime ideal is a prime ideal, and therefore the map naturally goes in the opposite direction, and therefore this map F is a map of commutative rings, but what I am trying to show is that the direction automatically reverses. even though the map goes from R to S, here the map goes from spec S to spec R. So therefore I have to write it is a functor from C rings op to top. Now here comes a definition, okay. So definition like f from C to D, this is a functor is called a covariant functor. Covariant means it doesn't change direction of arrows on C. And a functor and a covariant, okay, let me make it precise, and a covariant functor G from C op to D is called a contravariant functor on C. So normally we will try to avoid talking about it by specifying the domain and codomain categories, but this is the standard practice, okay. So standard practice says that I will give you a contravariant functor on category of sets, which means I am giving you a functor from sets op to something else, okay. So that you have to always remember. Covariant and contravariant will, in this course, will mostly try to avoid it, but sometimes like things just happen. But we are not going to say it's a contravariant functor on C op. Contravariant functor on C is a covariant functor on C op. Equivalently, you can also think of this G as a functor from C to D op. Yeah, only on one of the categories you have to reverse the direction of the arrows. I am going to give you one thing to think about here, yeah. So these are power set functors. So there is two of them, yeah. So this is P from the category of sets to the category of sets. So what does it do? I mean, naturally PA and this will go to the power set of B. And now if I am given a function f from A to B, where will it be mapped to?
The range function, the image of
The image? Yeah, so if you take an element A prime, yeah, I mean this is PF, if this belongs to this, then where will it be mapped to?
image of
F of A prime, yeah, the image of A prime under F. And this is fine, yeah, I mean you can check that this is a functor. But at the same time, there is also another functor, and I am not going to complete it yet. So this is PA and this is PB. And whenever I am given this F, then I can pull something back. I can take the inverse image, not just the direct image, but I can take an inverse image. So if I am given some B prime in PB, I can associate to it F inverse of B prime, which is a subset of A. So this map actually goes in the reverse direction. So I can think of it as a functor from sets to sets op or sets op to sets, but these are two different functors. So this one is called the covariant power set functor, this is called the contravariant power set functor, and they are very different, yeah. I mean you can see that this direction, sense of direction is already inbuilt in our mathematics. Inverse image has to do with reversing the arrows, yeah, and not preserving the arrows, okay. So therefore I said power set functors, there are two of them. Okay. There is one more functor that I want to talk about. Now, every functor from category, so suppose, let me keep track of the count. Suppose f from C to D is a morphism in cat. Then I can define f op from C op to D op. What does it do? Well, it takes an object and it maps it to itself. I mean, whatever f does on objects, you repeat that. Whatever f does on object, you repeat that. And suppose there is a morphism over here, where will you send it to? F of f op.
Yeah, this F must have come from a morphism from B to A in C. And then capital.
So Fa to Fb there is a morphism Ff, right? First of all, make sure whatever I have written is correct. Have I written it correctly?
F of whole of.
See, I said that let F be a morphism from A to B, but every morphism in C op is already of the form op of something. So I should not be writing this actually. I should be writing F op over here. So where is F, little f? Little f is in, yes, no, little f is in C. Okay. Corresponding to that, what do I have? Ff from Fb to Fa in D. And corresponding to this Ff, what do I have? Ff op from Fa to Fb. Okay, so what is the ultimate expression? Capital F op of small f op is equal to Ff op. But you can see after doing so many ops, ultimately this functor itself is covariant. Okay, so therefore, what I am saying that op from cat to cat is a covariant functor. Okay, despite doing so many ops. Okay, so here you are confused. Yeah, so this is actually an exclamation mark.
So, sir,
Uh-huh.
F of is same as F small f of.
Yes, that's what we did. We started with a morphism little f op from A to B in C op, which means it corresponded to a morphism f from B to A in C. Associated to that, we already have a morphism ff from Fb to Fa, and now you simply treat it as the opposite morphism. Okay, so if functors are generalizations of functions, then we should have a natural notion of injectivity and surjectivity, but it's not that simple. Yeah, we need something in more detail, something happens locally for injectivity and surjectivity. So those properties are called faithful functors and full functors. So we'll look at them next time. Yeah?
So this square which we drew,
Uh-huh.
that is not needed for the conclusion that op is covariant, huh? Because we have already defined f op from C op to D op.
Uh-huh.
At that statement itself, we get that op is a covariant.
Yes, but I mean, ultimately I have to draw the square to convince everybody that the directions are indeed correct.
And is it saying that the diagram commutes necessary?
There is no diagram here. When I am writing, this is actually a very good question. When I am writing, yeah, I mean, please pay attention to these arrows. These arrows, they all have a tail, vertical line at the tail. That means assignment. There is no diagram here. Yeah, that's the important property of a functor. There is no correspondence between this object in this category and this object in this category. It's plainly just an association of this object to this object. Okay, no function between them. This is the thing that you have to put in your brains. It's just association which behaves well with respect to morphisms and composition, the kind of structure that you have in both categories. There is no commutative diagram here. Commutative diagrams will have only arrows, and commutative diagrams only work in a particular category. You should be working in a single category, but there is not a single category here. Yeah, little f is not a morphism in cat. Okay, let's stop.